Welcome 爱学习的你 aboard. Your learning journey starts now. We are presented with a challenge: how to best cultivate reasoning in language models, particularly when we seek to scale their capabilities efficiently. Let us examine a novel approach, one that shifts our focus from the model's own problem-solving prowess to its capacity to teach others. It seems the common path, using reinforcement learning, often stumbles upon a significant hurdle: exploration. The model must already possess some nascent ability to solve a problem before it can learn effectively from sparse rewards. This reliance on initial capability, especially for complex tasks, raises questions. Furthermore, while these models are trained, their true utility often lies in guiding students, yet the process of distillation feels cumbersome, requiring powerful teachers and careful refinement. Does the goal of training the teacher align perfectly with the task of teaching the student? It appears there might be a disconnect here. Could we then consider a different perspective? Instead of demanding a model solve problems entirely on its own, what if we train it specifically to be a good teacher? Its primary task would be to generate clear, instructive explanations, assuming the solution is already known. This mirrors the role of a human teacher, who doesn't need to discover theorems anew but rather explains how to arrive at them. By focusing on this teaching role, might we sidestep the difficult exploration phase inherent in traditional reinforcement learning? Let us explore this idea further. So, how do we define this teaching task? The proposal suggests a simple yet profound shift. We provide the model not only the question, but also the correct answer. The model's task is then to connect the dots, to craft a detailed explanation that bridges the gap between the question and the known solution. As you can see in Figure 2, this contrasts sharply with the traditional RL format where the model must solve the problem independently. Is this simpler task, this connect-the-dots exercise, a more effective way to train a specialized teacher? To guide this teacher effectively, we need a reward function. What should we reward? Clearly, we want the explanation to help the student learn. But simply maximizing the likelihood of the final answer isn't enough. A teacher could just repeat the answer, which wouldn't constitute a meaningful lesson. Therefore, the proposed reward function has two parts. One part, R sub I superscript SS, measures the student's success in understanding the solution given the teacher's explanation. The other, R sub I superscript KL, ensures the explanation itself is logically sound and interpretable by the student. How might these two components work together? Let's first consider R sub I superscript SS. Its purpose is straightforward: to ensure the teacher's explanation is genuinely helpful. We take the teacher's explanation, feed it along with a question to a student model, and then measure how well the student predicts the correct solution. If the student understands the explanation, it should be able to reach the correct answer. The formula uses both average and minimum log probabilities. Why might this combination be important? Could it be to ensure that even the most challenging parts of the explanation are understood, rather than just the easy parts? Now, the second component, R sub I to the power of KL. This addresses the potential flaw in relying solely on student success. It asks, does the explanation make sense in the student's mind? It compares the distribution of the explanation tokens generated by the teacher when it has access to the solution versus when it only has the question. If the explanation is truly logical, the teacher's generation should be similar to what the student might generate based on the question alone. Using KL divergence here quantifies this difference. Does this term encourage the teacher to produce explanations that are not just statistically likely but also coherent and understandable? These two rewards are combined, with a weighting lambda, to form the overall RLT reward. This balance is crucial. We want explanations that help the student, but also explanations that are themselves logical and interpretable. The training objective then uses this reward within a standard reinforcement learning framework like GRPO. Notice the advantage highlighted: the dense nature of this reward. Unlike the sparse correctness signals in traditional RL, this provides continuous feedback, potentially making learning more stable and efficient. Does this dense signal fundamentally change the learning dynamics? How was this RLT concept put to the test? The authors trained their 7 billion parameter RLTs on a dataset of approximately 17,000 math and coding problems. They started with a 7 billion parameter Quen model, performed a brief supervised fine-tuning to get it accustomed to the new teaching format, and then applied the RLT training objective, using another 7 billion parameter model as the student for reward calculation. Crucially, the resulting explanations were used directly for distilling student models without the extensive post-processing seen in many prior methods. What might be the implications of this direct use of raw outputs? The results presented are quite striking. As Table 1 shows, students distilled from the raw outputs of a small 7 billion parameter RLT outperform students trained using distillation pipelines involving much larger models, such as DeepSeek Roan or QWQ32B, and even those with careful post-processing. This holds true across different data sizes, and even when the RLT is used to train a much larger 32 billion parameter student. Does this suggest that the RLT approach, by focusing on the teaching quality, produces inherently superior distillation data regardless of the student size? What does this imply about the efficiency of the RLT training process itself? Beyond just distilling students, the RLTs also show promise in providing better starting points for traditional RL. Table 2 compares cold starts using data from the RLT-7B versus other baselines. Again, the RLT-generated data leads to significantly better performance after subsequent RL training. This is particularly interesting when comparing against an RL-trained 7B teacher, which requires 2 rounds of expensive RL. The RLT provides a superior initial state for the next round of RL, even surpassing post-process traces from larger models. Could this mean RLTs offer a more efficient way to bootstrap the entire RL process? Perhaps the most intriguing finding is the zero-shot transferability. The RLTs, trained on math and coding problems, were applied to generate explanations for a completely different domain, the countdown arithmetic game. Students distilled from these RLT-generated traces performed remarkably well, even outperforming students trained directly on the countdown task using RL. This suggests that the RLTs have learned a more general skill of explanation generation, rather than being overly specialized to their training domain. Does this indicate a fundamental shift in how we think about training models for reasoning? To understand why the RLT approach works, let's look at the reward function itself. An experiment was conducted where the RLT generated multiple explanations for the same problem before any RL training. These explanations were then ranked by the RLT reward function. The results, shown in the right bar plot of Figure 4, reveal a strong correlation between the rank assigned by the reward function and the actual performance of the student models trained on those explanations. This strongly validates the effectiveness of the RLT reward function in predicting the quality of the teaching data. Does this correlation give us confidence in the design of the reward function? Looking closer at the explanations themselves, as shown in Figure 5, reveals qualitative differences. The RLT explanations often appear more grounded in fundamental principles, providing clearer logical steps. In contrast, some of the R1 traces, particularly those scoring lower on the RLT reward, seem to rely on external tools or exhibit patterns that might not generalize well, like brief humorous comments. The RLT explanations, however, seem to offer a more robust and structured learning path. Does this suggest that the RLT reward function successfully guides the teacher towards producing more pedagogically sound explanations? What happens if we remove parts of the RLT reward function? The ablation studies provide valuable insights. Removing the KL divergence term, which enforces interpretability, leads to a significant drop in student performance. The teacher essentially learns to cheat by repeating the solution tokens, failing to provide genuine guidance. On the other hand, removing the min/max reduction terms, which penalize low probability tokens and prevent overly long explanations, still yields decent student performance, but the teacher generates excessively long and repetitive explanations. This suggests that while the KL term is critical for pedagogical quality, the min/max terms help maintain efficiency and avoid certain types of degenerate solutions. Let's examine the example shown in Figure 11. Here, the RLT, trained without the KL term, is asked about printing n pages. The resulting explanation focuses heavily on the final formula, ceiling of n divided by 2, and repeats it many times. While the final answer is correct, the explanation lacks the crucial step-by-step reasoning that would help a student understand how the formula was derived. The student is presented with the result, but not the process. Does this illustrate why the KL term is so important for ensuring the explanation is genuinely instructive? Now consider Figure 12. This comes from the RLT trained without the min/max reduction terms. The explanation is extremely long, containing many semantically redundant steps. While it might eventually reach the correct answer, the sheer volume of unnecessary repetition could overwhelm the student and obscure the essential logic. The min/max terms seem to act as a regularizer, preventing the teacher from finding shortcuts that involve excessive length or redundancy. Does this highlight the importance of balancing the reward components to encourage both clarity and conciseness? So, we have examined this framework of reinforcement learned teachers. It seems to offer a compelling alternative to traditional reinforcement learning for reasoning, particularly by focusing on the teaching role. The empirical results suggest it can produce better distillation data, enable more efficient cold starts, and even transfer across domains. Yet, the authors acknowledge limitations and point towards future directions, exploring concurrent training, scaling up the models, and applying it to even broader datasets. What further questions does this raise for you regarding the nature of teaching and learning in artificial systems? In conclusion, this work presents a thought-provoking approach. By redefining the objective of the teacher model, focusing on generating effective explanations rather than solving problems from scratch, it seems possible to achieve significant improvements in efficiency and effectiveness. The potential benefits of democratizing advanced reasoning techniques through smaller, specialized teachers are considerable. The journey of understanding continues, and perhaps this framework offers a valuable new lens through which to view the complex interplay of learning and teaching.